The use of hormones to promote growth in livestock is a regulated practice in the United States, with significant variations across different species. In the beef industry, growth hormones are commonly employed, typically administered through small pellets implanted under the skin of the animal's ear. Natural hormones such as estradiol, progesterone, and testosterone are utilized to enhance muscle growth, balance hormonal effects, and improve protein synthesis. Additionally, synthetic hormones like Trenbolone acetate, Zeranol, and Melengestrol acetate are used to further promote lean muscle development and manage reproductive cycles in heifers. In contrast, the dairy industry focuses on hormone use to increase milk production rather than meat growth. Recombinant bovine somatotropin, rbST, a synthetic version of a naturally occurring hormone, is used to extend the lactation cycle of dairy cows. While growth implants are also approved for sheep, their usage is less prevalent compared to beef cattle, with Zeranol being the most common hormone for improving weight gain in feedlot lambs. Regulatory nuances highlight that hormones are banned in poultry and pork production in the U.S., with growth achieved through selective breeding. Additionally, hormones are prohibited for veal calves, reflecting a stringent regulatory environment aimed at ensuring animal welfare and food safety. Natural hormones, also known as bioidentical or endogenous hormones, are substances that are molecularly identical to those produced in mammalian bodies. Initially isolated from animal tissues in the early 20th century, modern natural hormones used in beef implants are predominantly synthesized from plant-based precursors, ensuring purity, safety, and large-scale production. Estradiol, historically sourced from the urine of pregnant mares or cow ovaries, is now produced through semisynthesis using phytosterols from soybeans or wild yams. This process chemically converts these plant fats into estradiol, which is identical to the estrogen produced by human ovulation. Similarly, progesterone was originally isolated from the corpus luteum of pigs or cows, but is now synthesized from diosgenin found in wild yams or stigmasterol from soy. This transformation occurs through a chemical reaction known as marker degradation, resulting in progesterone indistinguishable. Testosterone, which was initially extracted from bull testes, is now synthesized from cholesterol or plant sterols. Although the molecule is an exact replica of what bulls produce, the manufacturing process employs advanced fermentation and chemical engineering techniques using plant-derived materials. The shift away from direct animal extraction for hormone production is driven by three key medical reasons. First, the concentration of hormones from animal sources is inefficient, requiring thousands of bull testes for a small amount of testosterone, whereas plants offer a virtually limitless supply. Second, animal-derived hormones may carry biological contaminants, while plant-synthesized hormones are chemically pure. Lastly, the synthesis of hormones into esters allows for a slow release over extended periods, which is not feasible with raw animal extracts. In summary, the evolution of hormone sources reflects a significant transition from animal-derived origins to modern pharmaceutical methods utilizing plant-based materials, enhancing efficiency, purity, and stability in hormone production. The medical community does not conduct traditional clinical trials involving high doses of hormone-treated meat due to ethical concerns. Instead, it relies on risk assessments, toxicological studies, and epidemiological evidence to evaluate the safety and health impacts of such substances. In the late 1990s and early 2000s, the European Union commissioned 17 significant studies to support its ban on hormone-treated beef. These studies examined the genotoxicity of estradiol and the metabolic pathways of synthetic hormones like Trenbolone and Zeranol. The EU Scientific Committee concluded that no safe level of these hormones could be established, as even minimal residues could act as tumor initiators or promoters, particularly in prepubertal children. Concerns regarding growth hormones, such as recombinant bovine growth hormone, rbGH, used in dairy, primarily focus on insulin-like growth factor, IGF-1. Research indicates that individuals consuming dairy from rbGH-treated cows may exhibit slightly elevated IGF-1 levels, which are associated with increased risks of breast, prostate, and colorectal cancers. Epidemiological studies have observed a trend of earlier onset of puberty in girls, particularly in the US compared to the EU. Clinicians hypothesize that cumulative low-dose exposure to estrogenic residues in meat and dairy may contribute to this trend, although isolating direct causation from other factors, such as obesity, remains challenging. A summary of clinical research highlights that risk assessments by the FDA and JECFA found hormone residues to be negligible compared to endogenous production. Toxicological studies in the EU identified estradiol's potential to induce DNA damage, while epidemiological studies suggested links between IGF-1 levels and hormone-sensitive cancers. Additionally, observational data indicated that hormone residues in cattle excretion disrupt the hormones of wild fish. Regulatory safety assessments by the FDA are based on no observed adverse effect levels, NOEL, in lab animals, while the EU adopts a precautionary approach, considering the potential for long-term hormonal disruption in sensitive populations, such as women over 55 and children. Looking ahead to 2025, concerns about hormone potency highlight that synthetic steroids like Trenbolone acetate possess 8 to 10 times the anabolic activity of natural testosterone. Environmental studies reveal that hormone residues in cattle excreta contaminate groundwater, adversely affecting the fertility of wild fish and ecosystem. Consumer health concerns are rising, linking low-level hormone residues to increasing rates of breast and prostate cancer, obesity, and thyroid disease. Industry proponents argue that a serving of beef contains significantly less estrogen than a serving of broccoli, which is high in phytoestrogens. Xenoestrogens, also known as environmental estrogens, are synthetic or natural compounds that mimic the structure of 17-beta-estradiol, the primary female sex hormone. They can bind to estrogen receptors in the body, leading to inappropriate signaling that may disrupt hormonal balance. Unlike phytoestrogens, which are plant-derived and generally beneficial for women over 55, xenoestrogens are considered harmful due to their difficulty in being metabolized and their potential to cause estrogen dominance. Xenoestrogens are a subset of endocrine-disrupting chemicals, characterized by their synthetic origins, such as BPA and phthalates, and their bioaccumulative nature, meaning they can remain stored in body fat. In contrast, phytoestrogens are natural, biodegradable, and typically provide a weak but protective hormonal. The health impacts of xenoestrogens include metabolic disruption, weight gain, mood shifts, and increased risks of hormone-sensitive cancers due to their strong and disruptive signaling. Common sources of xenoestrogens include plastics, agrochemicals, industrial byproducts, and personal care products. Notable examples are BPA, found in canned foods and water bottles, and phthalates used in food packaging and cosmetics. For individuals aged 55 and older, exposure to these chemicals can lead to significant health issues, including metabolic disruption, skin sensitivity, and competition with beneficial phytoestrogens, ultimately hindering the health benefits associated with plant-based estrogens. To maintain a healthy hormonal balance, it is crucial to reduce exposure to xenoestrogens while increasing the intake of phytoestrogens from natural sources. To reduce exposure to harmful chemicals, several practical steps can be taken. The glass rule advocates for replacing plastic food storage and water bottles with glass or stainless steel alternatives. It is crucial to avoid microwaving plastic containers, as heat can accelerate the leaching of BPA into food. Additionally, checking the recycle code on plastics can help identify those more likely to contain harmful substances, specifically codes 3, 6, and 7. Using a high-quality water filter, such as reverse osmosis or carbon filters, is recommended to eliminate agricultural runoff and industrial chemicals from drinking water. Opting for organic meat and dairy products labeled as hormone-free can also minimize exposure to synthetic growth promotants prevalent in industrial farming. Recent clinical research into agrochemicals like atrazine and DDT has shifted focus towards their potential for low-dose endocrine disruption. Atrazine, a widely used herbicide, has been shown to trigger the aromatase enzyme, which converts androgens into estrogens. This effect can lead to health issues, such as estrogen dominance in women over 55, increasing the risk of breast and uterine tissue overgrowth, and declining sperm quality and prostate health in men. Atrazine's mobility in soil often results in its presence in municipal tap water, leading to chronic low-level exposure. DDT, although banned since 1972, remains a persistent organic pollutant that can affect health across generations, with research indicating that exposure in grandmothers may increase obesity and early puberty risks in granddaughters. The metabolite DDE, produced when the body breaks down DDT, acts as a potent anti-androgen, disrupting male hormone function. Agrochemicals pose several health risks, including metabolic issues, thyroid dysfunction, increased cancer rates, and liver stress due to the body's need to detoxify these synthetic mimics. Given that water is a primary route for atrazine exposure, using a certified filter for pesticide removal, such as the Brita Hub countertop water filtration system, is essential for reducing contaminants. Industrial byproducts like PCBs and dioxins are classified as legacy pollutants, remaining in the environment and human fat tissues for decades despite their ban in the late 1970s. These substances are among the most potent xenoestrogens, capable of permanently altering cellular responses to hormones. PCBs, once used in electrical transformers, contaminate soil and water, accumulating in the food chain, particularly in large fish and fatty meats. Dioxins, produced as unintentional byproducts of industrial processes, are considered some of the most toxic man-made chemicals. The text outlines significant clinical health impacts associated with exposure to certain chemicals, particularly PCBs and dioxins. These substances are known to suppress the immune system, disrupt thyroid function, promote hormone-sensitive cancers, and negatively affect skin health, leading to conditions such as chlorisine and reduced skin elasticity. To mitigate the accumulation of these toxins in the body, a detox protocol is recommended, focusing on dietary changes. Key strategies include trimming visible fat from non-organic meats, avoiding large predatory fish, and opting for lean proteins like wild-caught smaller fish and grass-fed meats. Cruciferous vegetables such as cabbage and broccoli are emphasized for their role in supporting liver detoxification through the metabolization of industrial toxins. The detoxification process is not merely about juice cleansing. It involves providing the liver and gut with specific nutrients to effectively eliminate these harmful chemicals. Since PCBs and dioxins are fat-soluble, they necessitate a robust phase 2 liver detoxification process, supported by high-quality fiber to prevent reabsorption in the intestines. The text also details specific nutrients and their food sources that can neutralize various toxins. For instance, glucosinolates found in broccoli and Brussels sprouts help make PCBs water-soluble for excretion, while chlorophyll from spinach and parsley binds to dioxins in the digestive tract. Sulfur compounds in garlic and onions support the body's antioxidant defenses, and indole-3-carbinol from cruciferous vegetables. Additionally, soluble fiber from fruits and vegetables acts as a sponge to absorb general residues. Overall, the body employs a three-phase filtration system to manage the detoxification of meat residues in xenoestrogens, highlighting the importance of dietary choices in reducing the body's toxic burden. The process of internal detoxification occurs in three distinct phases, each with specific functions and required tools. Phase 1, known as transformation, involves the liver utilizing oxygen and enzymes to unlock fat-soluble toxins supported by supplements like NAC and B vitamins. Phase 2, or conjugation, sees the liver attaching a handle to toxins, making them water-soluble, with DIM and calcium D-glucarate as essential tools. Finally, Phase 3, elimination, is where neutralized toxins are expelled from the body through bile or urine, facilitated by fiber and water. Detoxifying supplements play a crucial role in enhancing these phases. NAC, N-acetylcysteine, is highlighted as a gold standard for boosting glutathione, vital for phases 1 and 2. Effective formulations include Now Foods NAC 600 mg, which combines selenium and molybdenum to enhance liver detox enzymes. For optimal absorption of glutathione, medical professionals recommend liposomal or stabilized forms, such as Carlisle liposomal glutathione 500 mg. Additionally, Now Glutathione 500 mg, which includes milk thistle extract and alpha lipoic acid, serves as a comprehensive master regulator for detoxification. Specific supplements target various toxins. For plastics and parabens, calcium D-glucarate and high surface area fiber, like Garden of Life raw organic superfood fiber, are recommended to bind toxins in the gut. Chlorella, particularly Nutricost chlorella powder, is effective against herbicides and industrial byproducts, binding to harmful pollutants and heavy metals. For residues from meat, cruciferous concentrates such as NOW Foods DIM 200 provide necessary compounds to neutralize synthetic hormones. Overall, detoxification is emphasized as an ongoing maintenance task rather than a one-time event. Combining cruciferous vegetables with high-quality binders like fiber and chlorella creates an effective pathway for eliminating industrial chemicals from the body. Sulforaphane is recognized for its indirect antioxidant properties, primarily by activating the body's detoxification systems, specifically the phase 2 enzymes in the liver. To maximize sulforaphane production, it is recommended to follow the chop and wait rule, which involves chopping cruciferous vegetables like broccoli or cabbage and allowing them to sit for 40 minutes before cooking. This waiting period enables the formation of sulforaphane, which then becomes heat stable. Additionally, incorporating mustard seed powder into cooked broccoli can help reactivate sulforaphane that may have been diminished during cooking. Broccoli sprouts are noted for their extremely high sulforaphane content, containing 10. Regular broccoli also has a high sulforaphane potency, with steaming for less than 5 minutes being the best cooking method to preserve the enzyme, while boiling can destroy it. Brussels sprouts are another excellent source, providing significant fiber that aids in the elimination of spent hormones. Kohlrabi offers a medium level of sulforaphane and can be consumed raw in salads to enhance enzyme activity. Cauliflower, while lower in sulforaphane than broccoli, still contributes a meaningful amount. Mustard greens, with their medium to high sulforaphane content, provide a spicy flavor due to the presence of the enzyme that triggers sulforaphane production. Indole-3-carbinol, I3C, known as the hormone balancer, converts into diindolylmethane, DIM, in the acidic environment of the stomach. DIM plays a crucial role in guiding the liver to favor the safer estrogen metabolism pathway 2OH over the riskier one, 16OH. Various foods are rich in I3C, each offering unique health benefits. Garden cress, with the highest I3C content, is often overlooked but is excellent for enhancing hormone-friendly meals. Kale, which has very high I3C levels, supports skin elasticity and aids in liver detoxification. Both red and white cabbage are high in I3C, with red cabbage providing additional skin protection through anthocyanins. Bok choy is also high in I3C and is easily digestible, while arugula and radishes offer medium levels of I3C, contributing to digestive health and liver support, respectively. The conversion of I3C to DIM is significant as it helps the body eliminate synthetic hormone residues from meat, thereby preventing hormonal buildup that can lead to cystic breakouts, particularly during hormonal fluctuations. In addition to I3C and DIM, sulforaphane from broccoli sprouts activates the NRF2 pathway, promoting detoxification and anti-inflammatory effects. Cabbage, a cruciferous vegetable, is particularly noted for its cancer-fighting properties and is recommended for detoxification, anti-aging, and hormone regulation due to its fiber and vitamin C content. Conversely, romaine lettuce is highlighted for its high vitamin A content, making it beneficial for eye health and easier to digest for those with sensitive stomachs. Overall, cabbage is a superior choice for those focused on skin and immune health, while lettuce serves as a refreshing option for hydration and nutrition. Steroid hormones and protein peptide hormones exhibit significant differences in their composition, stability, and mechanisms of action. Protein hormones, composed of chains of amino acids, are water-soluble and are digested in the stomach, which inactivates them. This necessitates alternative administration methods, such as injections for insulin in diabetics. In contrast, Steroid hormones, derived from cholesterol and fat-soluble, maintain stability in the acidic environment of the stomach, allowing them to be effectively absorbed when taken orally, as seen with birth control pills. The entry mechanism into cells further distinguishes these two hormone types. Steroid hormones can easily cross the lipid bilayer of cell membranes and bind to receptors located within the cytoplasm or nucleus, leading to slower gene expression altering effects that may take hours or days. Conversely, protein hormones cannot penetrate the cell membrane and instead bind to receptors on the cell surface, triggering rapid responses through second messengers like CAMP. Additionally, steroid hormones require protein carriers for transport through the bloodstream, while protein hormones can circulate freely. These fundamental differences in structure and function underscore the diverse roles that steroid and protein hormones play in the body's physiological processes. Recombinant bovine somatotropin, rbST, is a protein hormone used in dairy cattle to increase milk production. Concerns about rbST in milk primarily stem from its classification as a protein hormone, which, even if not species-specific, is broken down into harmless amino acids during digestion, rendering it ineffective. In contrast, steroid hormones such as testosterone can remain active post-digestion, leading to stricter regulations by the FDA regarding their use in cattle. The characteristics of steroid hormones differ significantly from those of protein peptide hormones. Steroid hormones are derived from cholesterol and can be effective when taken orally, whereas protein hormones like rbST are made from amino acids and are ineffective when ingested due to digestion. Additionally, steroid hormones are synthesized on demand and have a longer half-life, while protein hormones are stored for quick release and have a shorter half-life. While major health organizations, including the FDA, WHO, and AMA, assert that milk from rbST-treated cows is safe for consumption, there are ongoing debates among researchers and international bodies, particularly in the European Union, EU, and Canada, regarding potential long-term health effects. Current scientific discourse continues to explore the implications of rbST milk consumption on both men and women, highlighting the need for further research in this area. The effects of rbST milk on men's health primarily raise concerns regarding prostate health. A significant issue is the relationship between insulin-like growth factor 1, IGF-1, and prostate cancer. Research indicates that rbST treatment in cows leads to increased levels of IGF-1 in their milk, and some epidemiological studies suggest a correlation between elevated IGF-1 levels in humans and a heightened risk of developing prostate cancer. There is an ongoing debate about the bioavailability of most regulatory agencies maintain that IGF-1 is a protein that is broken down during digestion, implying that it should not significantly elevate the levels of IGF-1 already produced by the human body. Additionally, the rbST hormone is species-specific, meaning that even if ingested directly, it cannot bind of rbST milk on women primarily revolve around concerns related to reproductive health, particularly in the context of breast cancer and puberty. Research indicates a potential link between elevated levels of IGF-1, a growth factor associated with rbST, and an increased risk of. This is due to IGF-1's role in promoting cell division and inhibiting apoptosis, which may theoretically facilitate the growth of existing mammary tumors. Additionally, there has been historical speculation regarding the influence of hormones in dairy products on the trend of early puberty in girls. However, extensive studies have largely failed to establish a direct causal relationship between rbST and the decreasing age of menarche. Experts suggest that factors such as childhood obesity and overall caloric intake are more significant contributors to this phenomenon. Concerns have also been raised about the impact of high growth factor levels, including IGF-1, on endometrial health, particularly regarding the risk of endometrial hyperplasia. Nonetheless, the evidence surrounding this issue remains inconclusive, indicating a need for further research to clarify these associations. The text outlines the differential impacts of rbST, recombinant bovine somatotropin, on men and women, focusing on various health concerns. For men, The primary cancer concern is prostate cancer, with a potential link identified between high serum IGF-1 levels and tumor proliferation. In contrast, women face concerns related to breast and endometrial cancer, with a noted potential link to the growth of mammary ductal cells. Regarding reproductive impacts, there is no scientifically established effect of rbST on men, while there is ongoing debate about its possible association with earlier onset of puberty or menarche in women. Both genders exhibit similar hormonal activity responses, as rbST is inactive in human receptors for both men and women. This information highlights the need for further research to clarify the implications of rbST on health across genders. The debate between the scientific consensus and the precautionary principle highlights differing approaches to the use of recombinant bovine somatotropin, rbST, in dairy production. The scientific consensus, represented by organizations such as the FDA and AMA, asserts that there is no significant difference between milk from treated and untreated cows. They emphasize that the levels of insulin-like growth factor 1, IGF-1, present in milk are negligible compared to the amounts naturally produced by the human body daily. In contrast, the precautionary view, held by regulatory bodies in the European Union and Canada, advocates for a more cautious approach. These regions have opted to ban the use of rbST, citing concerns that even small increases in IGF-1 could potentially have cumulative effects over time, thereby prioritizing public health and animal welfare. This divergence reflects broader philosophical differences in risk assessment and regulatory practices between the regions. The dairy acne pathway outlines how milk from rbST-treated cows can exacerbate acne through three biological mechanisms. First, the increased levels of IGF-1 in such milk act as a growth signal, stimulating the proliferation of sebocytes, which leads to excess oil production and clogged pores. Second, dairy's high insulinemic index causes a rapid insulin spike, enhancing the bioavailability of IGF-1 while reducing IGF-BP3 levels, resulting in a pro-inflammatory state that intensifies the redness and pain of existing acne. Lastly, milk contains precursors to dihydrotestosterone, DHT, that can bind to androgen receptors in the skin, promoting further oil production and increasing keratinization, which contributes to pore blockage. Together, these factors create a triple threat that significantly impacts skin health. The text outlines the effects of various components found in dairy products on skin health, particularly in relation to acne. IGF-1, a hormone that stimulates sebocyte growth, is associated with increased oiliness and shine of the skin. Whey protein, known to elevate insulin levels, can lead to cystic and inflamed breakouts. Casein contributes to follicle clogging, resulting in the formation of whiteheads and comedones. Additionally, iodine present in milk can irritate the pore lining, causing pustules or rapid onset bumps. The text highlights that skim milk is often linked to more severe acne compared to whole milk. This is attributed to the removal of fat, which alters the hormonal balance, and the addition of whey proteins that significantly increase insulin levels. It is noted that the primary systemic effect is not due to rbST, a protein hormone that is largely digested, but rather the elevation of IGF-1 that circulates in the bloodstream, influencing skin conditions. The gastrointestinal system is significantly impacted by the consumption of rbST-treated milk, primarily due to the presence of IGF-1, which may survive digestion when protected by milk proteins. This survival can lead to increased gut permeability and potential localized effects on the intestinal lining. Elevated systemic IGF-1 levels have been associated with a higher risk of colorectal health issues, including polyps and adenomas, as it may act as a mitogen in the colon. In the endocrine system, IGF-1's structural similarity to insulin allows for interaction between their receptors, which can influence insulin sensitivity. High dairy intake, particularly from milk rich in growth factors, may lead to increased insulin release from the pancreas, potentially resulting in chronic hyperinsulinemia and insulin resistance, a precursor to type 2 diabetes. Additionally, disruptions in growth factor levels could theoretically affect the hypothalamic pituitary thyroid axis, although concrete clinical evidence in humans is limited. Regarding the skeletal system, IGF-1 plays a crucial role in bone metabolism by stimulating osteoblast activity, which is why dairy is often linked to improved bone health. However, excessive growth hormone levels can lead to acromegaly-like symptoms, raising questions about whether rbST contributes to subtle changes in bone remodeling. The liver, as the primary producer of endogenous IGF-1, faces a metabolic load when exogenous growth-promoting factors are consumed. Research is ongoing to understand how these dietary factors may influence conditions like non-alcoholic fatty liver disease, NAFLD, through the insulin signaling pathway. A systemic summary highlights the potential effects of these factors across various systems, with clinical markers such as colorectal biopsy counts for gastrointestinal effects, hemoglobin A1C for pancreatic effects, bone mineral density for skeletal effects, and liver enzyme levels for hepatic effects. It is essential to differentiate between correlation and causation, as current FDA assessments indicate that IGF-1 levels in rbST-treated milk fall within the normal range found in untreated milk, complicating the identification of rbST as a direct cause of these systemic health issues. Ractopamine is a synthetic beta-agonist feed additive, marketed under names such as Paylean, Optiflex, and Optiflex, primarily used to enhance leanness and weight gain in livestock, including pigs, cattle, and turkeys. While it is legal in the United States and some other countries, it faces bans in over 160 nations due to concerns regarding human, animal, and environmental safety. The primary function of ractopamine is to act as a metabolic modifier by stimulating beta-adrenergic receptors, which leads to increased protein synthesis and reduced fat accumulation, thereby improving feeding efficiency. However, its use is associated with several adverse effects in animals, including Downer syndrome, cardiovascular stress, heightened aggression, and increased mortality rate. In terms of human health, the potential risks linked to ractopamine are still debated. Concerns include possible cardiovascular issues, elevated heart rates, and poisoning, although the FDA considers the residues from ractopamine in meat products to be safe. Despite this, many countries have chosen to prohibit its use. Food safety agencies employ testing methods to detect ractopamine residues in meat products, ensuring compliance with safety standards. While the US FDA has approved ractopamine for use, it remains banned in the European Union, China, and Russia. It is important to note that ractopamine does not. Instead, it mimics the effects of adrenaline in the animal's body. Veal is considered a safe meat option, particularly concerning the use of growth hormones. The FDA enforces a zero-added hormone policy for veal calves, which are processed at a young age, resulting in significantly lower exposure to exogenous growth stimulants compared to adult beef cattle. Additionally, the natural hormone levels in young veal calves are typically very low. However, the safety profile of veal becomes more complex when considering antibiotic use. Statistics from the USDA indicate that bob veal and culled dairy cows have a higher incidence of antibiotic residue violations than standard beef. This increased risk is attributed to the early separation of veal calves from their mothers, which leaves them with developing immune systems that are more vulnerable to illness and may necessitate antibiotic treatment. To mitigate this risk, consumers are advised to seek out certified organic or raised without antibiotics labels. From a nutritional standpoint, veal is advantageous for heart health and is often recommended for individuals with specific medical conditions. It is significantly leaner than adult beef, containing 20-25% fewer calories and lower saturated fat. The fine muscle fibers in veal make it easier to digest, which is beneficial for those with sensitive digestive systems. Furthermore, veal is nutrient-dense, offering more protein per ounce than chicken or beef, along with high levels of B12, zinc, and iron. In summary, while veal is a safe choice regarding added hormones, consumers should be cautious about antibiotic use and consider the nutritional benefits it offers, particularly for heart health and digestibility. Zeranol, marketed as Raugro, is a synthetic estrogen analog used in the beef industry as an anabolic agent to enhance weight gain and feed efficiency. It is derived from zearalenone, a natural estrogenic toxin produced by fungi, and is significantly more potent than other endocrine disruptors, being approximately 100,000 times more estrogenic than BPA. In men, Zeranol disrupts the balance between androgens and estrogens, potentially leading to decreased sperm count and motility, feminization of male glands, and increased risks of hormone-dependent cancers, such as prostate cancer, due to its binding to estrogen receptors. For women, Zeranol's mitogenic properties raise concerns, particularly regarding breast cancer proliferation, as studies indicate it can stimulate the growth of breast cancer cells. Additionally, it may exacerbate obesity-related issues by enhancing leptin's tumor-promoting effects and influence skin conditions linked to hormonal changes. The effects of Zeranol on children are particularly contentious, with associations made to precocious puberty and premature closure of growth plates, which could result in reduced adult height. Regionally, Zeranol is approved in the United States and Canada, where authorities argue that residue levels in meat are too low to pose health risks. In contrast, the European Union and China have banned its use in food-producing animals, citing cancer risk concerns based on the precautionary principle. The beef industry maintains that Zeranol levels in meat are below the acceptable daily intake set by the WHO, while clinical perspectives highlight that even minimal exposure to endocrine disruptors can significantly affect hormonal signaling, especially during critical developmental periods.